Hello everyone. We will now begin our series of lectures on Chapter 5, which is on analytic trigonometry. As part of analytic trigonometry, we will learn how to verify trigonometric identities, different trigonometric formulas, and we will learn how to solve trigonometric equations. However, as part of this lecture, we will talk about verifying trigonometric identities, where we learn how to reduce a complex trigonometric expression to its simplest form and also verify that one trigonometric expression is the equivalent of another trigonometric expression. Here's what will be covered in this lecture. We'll start by using the fundamental trigonometric identities, which we learned previously, to verify other more complex identities. Previously, we learned about different basic trigonometric identities like the reciprocal identity, the quotient identities, the Pythagorean identities, and the even and odd function identities, if you recall. Now we are going to learn how to apply them to verify more complex identities. Secondly, we will show the equivalence of expressions containing both logarithmic and trigonometric functions. In other words, we are going to show that one trigonometric expression is the equivalent of another trigonometric expression. Let's review some of the basic identities that we learned in the previous chapters, because we need to know these fundamental identities well enough to apply them to verify other more complex identities. We'll start with the reciprocal identities. We know that sine and cosecant are the reciprocals of each other. So sine of x is equal to 1 divided by cosecant of x, and cosecant of x is 1 divided by sine of x. They are the reciprocals of each other. For cosine, secant is its reciprocal, so cos of x equals 1 divided by secant of x. Secant of x equals 1 divided by cos of x. For the tan, its reciprocal is cotangent, so tangent of x can be rewritten as 1 divided by cot of x, and cot of x can be rewritten as 1 divided by tan of x. So these are the reciprocal identities of trigonometry. Then we have a set of quotient identities. Under the quotient identities, we have tan of x equals sine divided by cos. So sine of x divided by cos of x is equal to tan of x, and cot of x equals cos of x divided by sine of x. Since cotangent is the reciprocal of tangent and tangent is equal to sine over cos, then we can write cot as cos divided by sine. Recall that in reciprocal, you just flip the numerator and the denominator to get the reciprocal of a certain value. Next, we have the Pythagorean identities, which says sine squared x plus cos squared x equals 1. 1 plus tan squared x equals secant square x, and 1 plus cot squared x equals cosecant squared x. We have to know each of these identities well enough because these get applied pretty often when verifying identities. Finally, we learnt about the even odd identities, where sine of negative x is the same as negative sine of x, cos of negative x equals cos of x, and tan of negative x equals negative tan of x. So sine and tan are odd identities. Cos is an even identity, where if you substitute a negative value of an angle, then the cosine ratio will not change from what it was when we used a positive angle. So whether it's a positive angle or a negative angle, the cosine ratio does not change. That's what an even function is. For cosecant, it's the same as sine. Secant is the same as cos, and cot is the same as tan. Let's first come up with a strategy to verify identities. In order to verify identities, we have to show that one side of the identity is the equivalent of the other side of the identity. So we'll be given two expressions on either side of the equal sign, and we have to show that even though they look different to start with, we can reduce them and bring them to be the same expression. So that's the exercise we will be going through, but the suggestion is that we always start with the more complicated expression. No matter which side it is on, start with the more complicated expression and apply the different basic trigonometric functions on that complicated side to reduce it and bring it to the same expression as on the other side of the identity. So if you substitute one or more of the fundamental identities on the more complicated side, we will be able to rewrite it in a form identical to that of the other side. So that's going to be the exercise we are going to go through step by step in order to verify identities. We will start with an example which uses a relatively simple identity, which is cosecant of x times tan of x equals secant of x. Now at first glance, the two expressions don't look the same at all. However, we can take the more complicated expression of the identity, apply some of the basic fundamental identities that we learned before to reduce the complicated side and bring it to match with what we have on the other side, which is secant of x. We will follow a step-by-step process. Now, cosecant of x, as we know, is the reciprocal of the sine function. So cosecant can be rewritten as 1 divided by sine, and tan can be rewritten using a quotient identity, which is sine over cos. So what we do is, in the next step, we start with the more complex expression, which is cosecant of x times tan of x, and rewrite it as 1 divided by sine of x to replace cosecant of x, and tan of x can be rewritten as sine of x divided by cos of x. And you can see at this point we can simplify this further. We can cancel out sine and sine will divide. Sine of x and sine of x will divide. We will be left with 1 divided by cos of x, which is secant of x. Correct? But let's go through the step-by-step process. So 1 divided by sine of x times sine of x divided by cos of x. They divide the numerator and the denominator by the common factor, which is sine of x. We are left with 1 divided by cos of x, and that is equal to secant of x. So we've come to show that cosecant of x times tan of x is the equivalent of secant of x. So this is the process that we are going to use as the identities will get a little more complicated. In the next example, we will be using factoring to verify an identity. The identity given to us is sine of x minus sine of x times cos squared x equals sine cube x. Now we see that the left-hand side of the identity has a more complex expression than the right-hand side. Therefore, we will start by applying the identities on the left-hand side, on the more complex expression, and try to reduce it to match with what we have on the right-hand side. Now, many times we may have to use the rules of algebra to factor out an expression. So on the left-hand side, we see the expression is sine of x minus sine x cos squared x. Sine x and sine x are common in both the terms here. We can factor that out. So we can write this as sine x, factor out the sine x, we are left with 1 minus cos squared x, and 1 minus cos squared x, if you recall, is equal to sine squared x, and sine squared x will multiply with sine of x to give us sine cube x. However, it is very important when you are asked to verify an identity, you have to show the step-by-step process how you have arrived at the final answer, how you have come to make both sides the same. You cannot do it in one step. That's not the process of verifying identities. You will not get full points unless you show all the steps. So let's go through the steps one at a time. We start with the identity. Write out your identity. Sine x minus sine x cos squared x equals sine cube x. In the next step, you'll be factoring out the sine x from both the terms, and you'll be left with sine x times 1 minus cos squared x. It says factor sine x from the two terms, but make sure that you are able to factor it correctly. And then in the next step, we substitute sine squared x for the expression within brackets above. So 1 minus cos squared x is replaced by sine squared x. From the Pythagorean identity, sine squared x plus cos squared x equals 1. Therefore, we can solve for sine squared x and get the expression 1 minus cos squared x, and that is the equivalent of sine squared x, correct? So that's how we replaced 1 minus cos squared x with sine squared x, and now you just multiply sine squared x by sine of x and end up with sine cube x, and that verifies the identity. The left hand side and the right hand side match. All right. Let's work on another example now. As we will see, the identities are becoming rather complicated. This one has fractions and addition of fractions. We have the identity given to us as sine of x divided by 1 plus cos of x plus 1 plus cos of x divided by sine of x equals 2 times cosecant of x. So this involves combining fractional expressions to verify an identity. We have fractional expressions here. We have to perform an addition of fractions. Therefore, you have to remember the rules of adding rational expressions. This addition has to be performed correctly in order to be able to get to the expression that we are looking for, which is 2 times cosecant of x. Now at this point we will see that we have to go through several steps over a few pages, few slides, in order to be able to get to the final answer where both the left hand side and the right hand side will be the same expression. Alright, so let's go through the steps here. The first step would be to rewrite this entire expression as is, and then we will take the left hand side, which is a more complex expression, and first we will add the two fractions. Now the denominators are not common. We have to find the common denominator, the LCD. What are the two denominators? One is 1 plus cos of x. The first fraction has a denominator which is 1 plus cos of x, and it's always a good idea to surround the expression with brackets. And the second denominator is sine of x. When we multiply sine of x by 1 plus cos of x, that becomes our LCD. Therefore, in the next step, we see the two fractions written with a common denominator, right? Sine of x times 1 plus cos of x for both the fractions. However, since the denominator changed for the first one, it was originally 1 plus x, we multiplied that by sine of x to give a common denominator. You have to multiply the numerator also with that same sine of x that you multiplied the denominator with. Otherwise, the fraction will have changed. To keep it the same equivalent fraction, you need to multiply the numerator also with what you multiply the denominator by, sine of x. For the second one, the initial denominator for the original fraction, the denominator was sine of x. When we gave it a common denominator, we ended up with sine of x times 1 plus cos of x. You have to multiply the numerator also by 1 plus cos of x, right? Now what happens in the next step is we have sine x times sine x. At this point, I'm just looking at the first fraction. Sine x times sine x is sine squared x, and sine x times 1 plus cos x remains in the denominator. For the numerator in the second fraction, 1 plus cos x multiplied by 1 plus cos x gives us 1 plus 2 times cos x plus cos squared x. This is the same as using the formula for a plus b whole squared, where it's the same as writing 1 plus cos x whole squared. So you can apply the formula for a plus b whole squared, which is a squared plus 2ab plus b squared. When you apply that on 1 plus cos of x, you should come up with 1 plus 2 times cos x plus cos squared x divided by sine of x plus sine of x times 1 plus cos of x. Since we have a common denominator now, we can add the numerator of both the fractions, and we will continue that in the next slide. So let's continue at this point. We have brought over the expression from the previous slide, which was sine squared x divided by sine x times 1 plus cos x plus 1 plus 2 times cos x plus cos squared x divided by sine of x times 1 plus cos of x. Since the denominators are common, we can put everything under a common denominator and write it as sine of x times 1 plus cos of x and combine the terms in the numerator as appropriate. So sine squared x plus 1 plus 2 times cos x plus cos squared x is what we have in the numerator. Now let's see if we can simplify the numerator further. There's nothing we can do with the denominator at this point. However, let's see if we can work further on the numerator. If you look at the terms, we see there's a sine squared x and there's a cos squared x, and that should immediately remind us of applying the Pythagorean identity, which is sine squared x plus cos squared x equals 1. Therefore, these two, sine squared x plus cos squared x, can be written as 1. And that's what is being done in the next step. Sine squared x plus cos squared x, they bring cos squared x next to sine squared x, so we can see that we can apply the Pythagorean identity here. Just replace this entire expression with 1 and we get 1 plus 2 times cos of x divided by sine of x times 1 plus cos of x. So the next will be where 1 plus 1 will be equal to 2. So we add the two ones, so we get 2 plus 2 times cos of x divided by sine of x times 1 plus cos of x. We see 2 in the numerator is the common factor, so we end up factoring that and writing it as 2 times 1 plus cos of x, and that's over sine of x times 1 plus cos of x. We can end up dividing 1 plus cos of x. We will be left with 2 divided by sine of x, and 2 divided by sine of x is the same as 2 times cosecant of x, right? So it still continues in the next slide, but let's see if that's what they do in the next few steps to arrive at the same expressions. So here's what we carried over from the previous slide, from the last step. 2 plus 2 times cos x in the numerator divided by sine of x times 1 plus cos of x. Next step should be to factor the common 2 from the terms in the numerator, which will give us 2 times 1 plus cos of x divided by sine of x times 1 plus cos of x, and 1 plus cos of x should divide in the numerator and denominator, and we will be left with 2 divided by sine of x, and that can be rewritten further as 2 times 1 divided by sine of x. 1 divided by sine of x by the reciprocal identity is cosecant of x. So just replace 1 divided by sine of x by cosecant of x and we end up with 2 times cosecant of x. We have just verified the identity. Let's get some more practice of verifying identities. Now there will be situations where you cannot just work with one side of the identity and reduce it and get the expression on the other side. There will be situations where you will have to work on both sides of the identity. Both expressions may be equally complicated and you may have to reduce them to the same expression. And this is an example of that. The identity given to us is 1 divided by 1 plus sine of theta plus 1 divided by 1 minus sine of theta equals 2 plus 2 times tan squared theta. We are going to begin by first handling the left-hand side of the identity, the expression on the left-hand side, reduce that to its simplest form, and then we will take on the other side of the identity, 2 plus 2 tan squared theta. Let's start with that. We begin by working with the left side. The left side is 1 divided by 1 plus sine of theta plus 1 divided by 1 minus sine of theta, which is equal to, we give the denominator, we have to combine the two fractions. So the common denominator here is 1 plus sine of theta multiplied by 1 minus sine of theta. That's a common denominator. And when we have the common denominator, we have 1 times 1 minus sine of theta for the numerator of the first fraction. Because we multiplied the denominator of the first fraction by 1 minus sine of theta to give it a common denominator, we have to do the same to the numerator as well. We have to multiply the numerator by 1 minus sine of theta as well. As for the second fraction, it's 1 minus sine of theta. The common denominator has a 1 plus sine of theta, so you have to multiply the numerator of the second fraction by 1 plus sine of theta as well. Let's see what happens in the next step. In the next step, we have in the denominator 1 plus sine of theta multiplied by 1 minus sine of theta. In the numerator, we have 1 minus sine of theta plus 1 plus sine of theta. So we can see here minus sine of theta plus sine of theta will zero out. We will end up with 1 plus 1, which is 2 divided by 1 plus sine of theta times 1 minus sine of theta. Right? So let's pull up the next step. It's 2 divided by 1 plus sine of theta times 1 minus sine of theta, and then we end up with 2 divided by 1 minus sine squared theta. When you multiply out 1 plus sine of theta times 1 minus sine of theta, it's the same as a squared minus b squared. If you recall, in algebra you had learnt a plus b times a minus b is equal to a squared minus b squared. The same thing happens here, but this time our expression is 1 plus sine theta times 1 minus sine theta instead of a and b. So it's 1 squared minus sine squared theta. That's how they ended up with this expression. We will now work with the right-hand side of the identity, which was 2 plus 2 times tan squared theta. The first thing that we do is replace tan squared theta by its equivalent, which is sine squared theta divided by cos squared theta. Recall we had learnt previously another basic identity, which was tan of theta equals sine of theta divided by cos of theta. If we square both sides of this equation, we will end up with tan squared theta equals sine squared theta divided by cos squared theta, and that is what we replace the tan squared theta by and rewrite the expression as 2 plus 2 times sine squared theta divided by cos squared theta. The next step will be to add the two terms. Now, the first term has a denominator of 1. That's why it's not visible. It has a denominator of 1. The second term has a denominator of cos squared theta. We have to find the common denominator, which in this case would be cos squared theta, and then we can add the two numerator expressions. However, because we have given the first term forced common denominator of cos squared theta, you have to multiply the numerator as well by cos squared theta to keep the fraction equivalent, to keep the value of the term the same as before. And then on the right hand side we have the same 2 times sine squared theta divided by cos squared theta. In the next step we rewrite the expression again with one common denominator of cos squared theta, and we can add the terms in the numerator, which is 2 times cos squared theta plus 2 times sine squared theta. We see 2 is a common factor in both the terms of the numerator that can be factored out, and we can rewrite it as 2 and then within brackets cos squared theta plus sine squared theta. And that's what's being done in the next step. They have factored out the 2 and then within brackets we have cos squared theta plus sine squared theta. Recall that the Pythagorean identity stated that sine squared theta plus cos squared theta is equal to 1. Therefore, we can replace this entire expression cos squared theta plus sine squared theta by 1, and we will end up with 2 times 1 divided by cos squared theta. Therefore, 2 divided by cos squared theta. Now this will continue in the next slide, so let's find out what the next steps would be. Let's go over the final steps of verifying the identity. In the previous step, we ended up with 2 divided by cos squared theta after replacing the expression cos squared theta plus sine squared theta equals 1. So we had in the numerator 2 times cos squared theta plus sine squared theta, and we recalled the Pythagorean identity which said sine squared plus cos squared equals 1. So we replace this entire expression within brackets by 1, and when we did that, 2 times 1 gave us a 2. So we reduced the entire expression and rewrote it as 2 divided by cos squared theta. In the next step, we are going to replace cos squared theta by 1 minus sine squared theta. How did we come up with 1 minus sine squared theta? Again, from the Pythagorean identity, because sine squared plus cos squared equals 1. If we solve for cos squared, we will end up with 1 minus sine squared. Therefore, we replaced the cos squared by 1 minus sine squared. Now we will go back to the left hand side of the identity where we had rewritten 1 divided by 1 plus sine theta plus 1 divided by 1 minus sine theta equals 2 divided by 1 minus sine squared theta, which is the same as what we got when we worked with the right hand side of the identity. We reduced that to 2 divided by 1 minus sine squared theta. Therefore, the left hand side now is equal to the right hand side, and we have completed the verification of the identity, and we've shown that both sides are essentially equal to each other. We will now work through an example which is about verifying if two expressions are equivalent or not. Now, the expressions given to us are a little bit different from what we've worked before because it involves taking the natural logarithms of different trigonometric ratios. As you can see over here, it says show that each pair of expressions is equivalent, and the pair is, one of them is ln of the absolute value of tan of x, and the other expression is this entire expression ln of the absolute value of sine of x plus ln of the absolute value of secant of x. So this entire expression is the second one, and we have to show that ln of the absolute value of tan of x is equal to ln of the absolute value of sine of x plus ln of the absolute value of secant of x. Now, why do we have the absolute value signs? Go back to the definition and properties of logarithms. We know that we can only take the logarithms of positive values, correct? And that's why it cannot be a negative ratio. They have the absolute value signs here around each of these trigonometric ratios. So let's go through the steps of showing that both these expressions are equivalent. In the first step, we rewrite ln of tan of x as ln of sine of x divided by cos of x. We have done this previously in verifying some of the previous identities. We replace tan of x by sine of x divided by cos of x, and we do exactly the same here as well. In the next step, we rewrite sine of x divided by cos of x as sine of x multiplied by 1 divided by cos of x. This is an equivalent expression for sine of x divided by cos of x. The next step, we know that 1 divided by cos of x is equal to secant of x, correct? This entire expression is the formula for secant of x. Therefore, we replace 1 divided by cos of x by secant of x, which is the reciprocal of cos. And now we go ahead and apply one of the properties of logarithms where we can rewrite a multiplication. So ln of sine of x times secant of x can be written as, let's write that property here. Remember that ln or log of x times y can be rewritten as ln of x plus ln of y, correct? And that's what is being done in the next step. We have ln of sine of x times secant of x. We can rewrite that as ln of the absolute value of sine of x plus ln of the absolute value of secant of x. And now we have shown that ln of tan of x can be rewritten as ln of sine of x plus ln of secant of x. Therefore, they are equivalent expressions. Here's another example where we need to verify if the two expressions are equivalent or not. The expressions given to us are minus ln of the absolute value of secant x plus tan of x, and the other one is positive ln of the absolute value of secant x minus tan of x. So what we have within the absolute values is that for the first one, we have a plus secant x plus tan of x. For the second one, it's secant x minus tan of x. Not only that, in the first expression, it's a minus ln, whereas in the second expression, it is just positive ln. All right, so we have to recall the properties of logarithms. When we have minus ln, that's the same as writing minus 1 times ln, which can be rewritten with the power. So we can write this entire expression as ln of the absolute value of secant x plus tan of x raised to the power negative 1. Again, please review some of the logarithmic properties, and you will see that that's how we work with the exponents of the logarithmic expressions. So what happens in the next step? We rewrite negative ln of the absolute value of secant x plus tan of x equals ln of the absolute value of secant x plus tan of x, but we transfer the negative before ln and write it as the power of what we have within the absolute values. All right. Now, what does an exponent of negative 1 mean? It means that it's the reciprocal of the expression secant x plus tan of x. And that's going to come up in this step here, where it's equal to ln of the absolute value of 1 divided by secant x plus tan of x. How did we get to write it in this form? Because of the negative 1. Negative 1 suggests the reciprocal of any value, the reciprocal of the expression to which the exponent has been raised to. Now, in the next step, we multiply the numerator and the denominator of this fraction by secant x minus tan of x. The whole idea is to square the secant x plus tan of x, square it up. So secant x plus tan of x multiplied by secant x minus tan of x. If we multiply the denominator of a fraction by any value or any expression, we have to do exactly the same thing to the numerator. So that's why you see both the numerator and the denominator being multiplied by the same expression. And what happens is secant x plus tan of x multiplied by secant x minus tan of x squares secant x and tan of x with a negative sign in between the two. So what we have now here, after the operation in the previous step, we have ln of the absolute value of secant x minus tan of x obtained by multiplying 1 by secant x minus tan of x. Now secant x plus tan of x times secant x minus tan of x is something we had learnt in an algebra class. A plus b times a minus b is equal to a squared minus b squared. So when we multiply secant x plus tan of x by secant x minus tan of x, we end up squaring secant, we square tan, and there's a minus sign in between the two. And then in the next step, we will have secant squared x minus tan squared x replaced by 1. We can use the Pythagorean identities to derive another identity, which is secant squared x minus tan squared x equal to 1. So you can do that on the side, and I can show you why secant squared x minus tan squared x will be equal to 1, because secant squared x can be written as 1 divided by cos squared x. Tan squared x can be rewritten as sine squared x divided by cos squared x. Because there's a common denominator, we can just subtract the numerator expression 1 minus sine squared x. 1 minus sine squared x is equal to cos squared x divided by cos squared x in the denominator will give us a 1. Right? We just verified that secant squared x minus tan squared x equals 1. Therefore, we can replace this entire expression by a 1. And what are we left with now? We have equal to ln of the absolute value of secant x minus tan of x. We will now talk about some general guidelines for verifying trigonometric identities. Now keep in mind that identities can be verified in different ways. People can take different approaches and still be able to verify the identities and prove that the two expressions are equivalent, are equal to each other. There are different approaches, different ways that one can go about the process of verifying identities. However, for us as starters, those who are starting in the process of verifying identities, these are some broad general guidelines which may give you some direction in going about how to verify the identities. The first one says work with each side of the equation independently of the other side. Start with the more complicated side and transform it in a step-by-step fashion until it looks exactly like the other side. And that's what we have been doing. If you observe the way we have been working through some of the other examples, we have been working with one side, the complicated side, and try to reduce it or simplify it and bring it to look like what we have on the other side. Then it says analyze the identity and look for opportunities to apply the fundamental identities. Again, we have done that for some of the previous examples. We've used the quotient identity, we've used the reciprocal identities, we have used the Pythagorean identities as well. And then it says try using one or more of the following techniques. Number 1, rewrite the more complicated side in terms of sines and cosines, because that helps. Try to transform a complicated expression and rewrite it in terms of sines and cosines. Now this may not always work, but you can try that approach. And number 2 is factor out the greatest common factor. There are more steps in the next slide, so let's go over that. So number 3 says separate a single term quotient into two terms. So if we have something like a plus b divided by c with a common denominator, rewrite it as a divided by c plus b divided by c. Distribute the common denominator to both the terms or to each of the terms and rewrite it as an expression. You can do the same for a minus b divided by c. And then number 4 says combine fractional expressions using the least common denominator. We did that too in the past. Number 5 says multiply the numerator and the denominator by a binomial factor that appears on the other side of the identity. And then finally, don't be afraid to stop and start over again, because verifying identities is very much like solving a puzzle. Many times you may proceed through the steps and then find that it's not getting you anywhere. You might have to go back and start all over again using a different approach. So these again are some of the broad guidelines, and as you work through more identities, as you work through the process of verifying identities, you will become more comfortable and you'll find it easier and even fun going through the steps and the process of verifying identities.